Hey, hi guys, good morning.
Yeah, Shrikant, good morning.
Good morning, good morning.
Shrikant, I have one question here.
Yeah,
In
go ahead.
this K nearest neighbor, I remember
Hmm.
initially you said that we should take K as an odd number
Yeah.
because that's the most optimal way of getting the highest accuracy. But
Mm-hmm.
later on in the Python script that you gave us, in that
Mm-hmm.
you have done a loop from K equals to 1 to K equals to 10.
Right.
So why is that?
See,
Why did you
yeah,
choose the numbers? You could have chosen plus one, no odd, all the odds.
right. See, the odd, k equal to odd, we will take it when we are mainly considering a binary classification problem. See, then only the tie may happen, right? When we have two classes and when we are taking even number, it can be possible that we will get a equal number of um, points falling in each of those classes. But the example what we have taken, that is multi-class classification where we have four categories, I suppose, right? So in that case, you can see, and in
Okay,
for
yeah.
iteration it would be easier, if you take the sequence of number rather than taking the odd numbers and then running the loop. So there's the reason I just took 8 k equal to 1 to 10. But if you are going through binary classifications, you just create a list of even numbers from 1, then put it 3, then 5, then 7, and then run the loop on that particular list. Okay, I just gave you the example that if you want to find out the best k value, then you have to iterate to multiple k values and see at which k value you are getting a better accuracy. Okay.
Okay, thanks. Yeah.
Yeah. Okay, so any other questions? All right, so we will do a quick revision of the naive Bayes, which we discussed in the last class. Okay, so can we try like this? Can anybody try? What is naive Bayes? Just have a try, okay? What we discussed in the last class, what you remember, what is naive Bayes? Anybody wants to try? Just give a try. Agwe, Agay,
Uh,
Harishri, Saurabh, anybody? Just you guys speak one line and we will be good, right? So collectively, that would be our answer for naive Bayes. So anybody wants to go first? So if somebody asks you, can you tell me about naive Bayes? Then how will you describe this algorithm? Go ahead, guys. There is no right and wrong answer, so I'm not going to penalize you for that. So whatever you remember, just speak it down. Okay, why don't you start?
actually, I didn't attend the Saturday class. I haven't yet to go through that
Oh,
actually.
is it?
I was off actually, so that's why.
Okay, no issues. Harishri, do you want to try?
Yes, sir. So it uses Bayes theorem in the backend to calculate the thing, and it is used for supervised algorithm. It is a supervised algorithm,
Mhm.
and it is mostly used for classification types.
Right, very good, very good. Okay, so yeah, so you have to be a little more confident. Okay, so all your points were correct, but I don't know, you were sounding little nervous, so you have to be more confident. I'm saying in the interview, it's all about your confidence, guys. Okay, even if you are saying the right, if you're giving the right answer, but if you are nervous, then the impression would be different, right? So, okay, so let's quickly revise. Naive-Bayes algorithm is a supervised learning algorithm which is based on the Bayes theorem and used for solving classification problems. So this is exactly what you said, Harishri. So that's uh, very good. So it is mainly used in text classification that includes a high dimensional training data set. So see, this is important. When I'm saying text classification, usually in the text data, there would be a lot of words, right? It's not something like, oh, you are dealing with 10 words, 15 or 20 words. Just imagine in the document, even if you remove the preposition, conjunction, or all the regular words, the important keywords also, if you count, it would be many. Okay, it would be several words. Okay, so it is considered as a high dimensional data set. So high dimensional means you will have more number of features. So typically it would be minimum 100 or 200 features, right? And if you want to have a algorithm which can quickly classify these documents, then Naive Bayes is should be your choice, right? So because it is quick and it can able to scale to that high to that level and can able to give you the accurate results. Oh, sorry. Okay, so naive-Bayes classifier is one of the simple and the most effective classification algorithm, which helps in building the fast machine learning models that can make a quick prediction. So that's what we discussed. It is also called as probabilistic algorithm or probabilistic classifier. So every algorithm will have a second name based on the way it works, right? So, for example, the KNN is also known as lazy learner or the lazy learning algorithm, or we also called as instance-based learning algorithm, because because it is not building any knowledge. Okay, basically, it is for every instance which it needs to predict, it is going to the training data set, and based on that, it is making predictions, right? Now, the naive Bayes is called as probabilistic based learning algorithm because underneath it is a Bayes theorem, which is a probability, conditional probability equation. So it considered that method, to calculate the probability. So in the interview, people may not ask directly like explain me naive Bayes, or they may ask you, okay, explain me one probabilistic based algorithm. So then you can pick this naive Bayes and then you can talk about. Okay, so like that, as we move forward, every algorithm will have its second name based on the way it functions, right? So, so it's called probabilistic classifier because it predicts on the basis of the probability of an object. And some of the popular examples, mostly the here we have listed all the text-based classification, but it can also use on the structural data, which we are going to discuss in today's class. Okay. So that is so you all these things why it is called naive because here we will assume that all because this algorithm assumes that all the input variables are independent. They are not conditioned on each other. They are not dependent on each other. That's the reason it is called as naive. Okay, and this is your Bayes theorem. Okay, so how it works is first it convert the any given data set into a frequency table. Frequency table means it will count that if this particular event has occurred these many times, how many times your outcome or the output event has occurred. Okay, based, and then it will find out all that likelihood probabilities of all the given features, and then based on the Bayes theorem, it calculates your output probability. Okay, so that's in brief about naive Bayes, and today we are going to discuss about one unique problem. And this is going to be a more exhaustive use case because here we will deal with a lot of things. So please follow me, and if you have any questions in between, let me know. Okay, so this is my data. Let me explain you what this data is all about. So here, this output column is something, okay, which we need to predict. So here, let me show you how much. So see how much data we have. We have around 32,561 data points. Okay, and here there is some information related to a person, and so all the demographic, age, gender, and all those things are there. And then finally, this is his income, that person's income. So basically, it is only two categories are there here. So whether this person's salary is less than equal to 50K or greater than equal to 50K. Now, this is a kind of a very generic solution which can be used by any domain, right? So because now the data is required by any business. Okay, if you go to the bank, banking people requires the data, something like that. Okay, based on the income level, they will call you and they will target some product or services. Okay, if you go to the retail, then they will also do some kind of marketing based on the person's income level. So predicting the income level is now becoming very important for every in every domain, so that they can target the customers or target that those people in a more efficient way. So if the income is high, they can position some expensive product or expensive services or premium services. If the income is less, then they can uh, target at a more economical products level and all those things. Okay, so now this is my data. Can anybody quickly tell me what is the issue with this data? There's something, do you see it's missing in this particular data?
So
You know,
like, I think the degree you see, it's alphabetic. Sometimes it's using numerical, I think.
this one? Okay, yeah,
Uh,
okay, okay. Anything else?
Labels.
Labels, exactly. So there is no header. Okay, so there is no header. Sometimes we get data like this. And anything else you are seeing? Any other issues in this data?
Null values.
yeah, a
Null
lot of null
value,
values.
lot of
Yeah,
null values.
KLL1, yeah.
And there is some kind of a special characters also, question mark, right? So, this is a completely raw and noisy data, okay, which you have received. And I must tell you, in most of the cases, the real data would look like this. You'll get lots and lots of data, but the quality of the data would be so poor that you need a lot of time, to improve the quality of that data set. Okay. Now, we will see that step by step how we can go and improve the quality of the data set first, and then apply this Naive-Bayes algorithm, to train the model. Okay, so here I am importing the data. Okay, now this is my data. Okay, so I have 32,560 rows and 15 columns. But if you print this, it will not give you the names, okay, of the columns. So here I'm passing the column names. Okay, I'm passing this list. And when you are and even in this particular step, you can even use, to rename the columns. Let's suppose in your data set, the names are not, what do you say, um, self-explanatory, or those are very complicated names. Okay, and you want to put a very simple names. Okay, so just pass the list. Okay, where you can define the names of every column. Okay, and then say data frame dot columns and pass that list. So what it will do is it will update the column names of the entire data set. So here, as I do not have the column names, I'm adding these columns, to my data set. Okay, so now I have the now if you see, I have the column names for every column now, and this is what my data set, which we have just seen. Okay, so I'm just if you say df head, then it will give you the top five, and if you say df dot tail, then it will give you the bottom five, and if you want to view more than five, then you can give index, okay, row indexes, and then it will give you that many number of rows.
So, Srinath,
Yeah,
what is this
but
FNL WGT column, the third column?
This is, I guess, final weight.
Okay.
Weight is what? Mm, okay, so I'll get back to you on this. This is a nice question. Age, work class, education, this is
So
all clear.
so how did you decide on the labels or the fields
Yeah,
that they
so
are
the
this only?
yeah, as you know that in the entire process, the second stage is about data understanding, right? So sometimes by usually, you do not get any data set without labels, but sometimes if you get it, then you need to understand what is this each column is all about. You have to talk to the SMEs, you have to talk to your data provider and say that, okay, you gave me the data, but you haven't given me the labels, right? So, or sometimes what will happen is you yourself, you need to understand what this data set is all about. See, when we look at the data, I think we can easily guess it, right? So this bachelor's, 11th bachelor's, it's talking something about education, right? This self-employed, private, public, it is talking about the work class. Whether the person is divorced or married, so it is talking about some marital status, right? So by looking at the data also, sometimes you can able to find out what labels it is. Otherwise, you have to go to the SME and then you have to name the labels. Okay. This FNL WGT, I am not sure what it is, but this is also describing some attribute of this person. Okay, so I will get back to you on that. Okay. Oh, okay. So this is done. Now I'm finding out looking at the summary of the data set. So df.info. So it will give you the total number of columns and total number of rows, and then it will also provide you the data type of each of these variables. So basically, you can understand the schema of this entire data. And we have seen, right, if you find this data type as incorrect, then you can go and use as type function, to convert that into an appropriate data type. Okay, now what we are doing is here there are multiple categorical variables and there are multiple numerical variables. So here what I'm trying to do is now here I'm segregating the categorical and the numerical variables, and here you will see that there is one specific method we will use to transform the categorical variable, and I will explain you why we have to do that and why it is important. Okay, so categorical, here, what I'm doing is for every variable in this df columns. So when you say df dot columns, it will print you the list of all the column names, right? And on that, I am running this for loop. So for var in df columns, if this particular column data type is equal to object, or in short, if it is equal to O, okay, then I am saving that into this particular object known as categorical. So if you see, there are now 9 categorical variables which it has identified: work class, education, marital status, occupation, and all those things. It has identified as categorical variables. We can, in fact, check it here also. So see, whichever variable has been defined as object, it has identified all those variables and then saved it in this particular object known as categorical. All right. So now, what I will do, I can filter it very easily now. So this categorical object has all those 9 column names, which are categorical. I'm just passing here inside the square brackets of this particular data frame. Now it has filtered all the categorical variables for me. Now I'm going and summarizing I'll this categorical variable. So for that, firstly, okay, so let me run this, okay, because I have rerun it. And see, in this DF info, sometimes you will get what do you say, misled by this information. See, here it is saying all 32560, 32560 for all the columns. So if you look at this, it may look like that there is no missing values. but we will see that there are no missing values. So by looking at this, we see that there are no missing value in this data set, but we will confirm this further, okay? But we have seen in the Excel file that there are certain missing values, right? So I'm running this. Yes. So these are my categorical variables. Now if I run this, here also all the categorical variable, it is showing as no missing values. So is null is a function which will check in every column, is there any kind of a null value? Null value means either it could be an NA means not a number, or it could be a blank, okay, blank cell. So if it finds any such kind of scenario in any of the variables, then it will give you the output as true. Okay, is null is just like a check condition. It is checking is there any null or not. If it finds any blank cell, then it will give you output as true. Otherwise, it will give you output as false. So like that for every column. Okay, let me go and print you this. See, for every column, it will check is this particular value is null or not null. So mostly it has given as false, 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 because even the question mark which we have seen in the table, it is considering it as a value. Okay, so we'll see that how we have to deal with that. So now in internally in Python, this false value is encoded as 0. Okay, internally, and the true value would be encoded as 1. So you can even apply the arithmetical calculation on this particular data. So that's what we have done here. So I'm saying dot sum. So what it will do is it will go and find out the sum of every column. In every column the values are false, so that's the reason you are seeing the sum as equal to 0. If there would have been any true in any of the columns, then you would have found some number here. Okay. Now what I'm doing is now next step. So this is step by step. I'm describing the data, I'm analyzing the data, and then in that particular process, a lot of discrepancies may come out. Okay. So what I'm doing is now is for every variable in this categorical object. Okay. So you remember, right? We have 9 variables names in this categorical list. Okay, so I am going and doing the count of the values. These are categorical column, right? So definitely the categories would be repeated. Okay, would be getting repeated in every column. So what I'm doing is with this particular line of code is I'm counting the unique characters categories, okay, in every categorical variable. So for example, the first work class, okay, in the work class, I have these all categories. I have private, self-employed, local government, and here is the catch. Okay, so there is one category, which is the question mark, in which there are 1836 observations. So for all these observations, the work class is not available. Okay, it's it is marked as question mark. So now I see the discrepancies. Okay, so if I have ignored this, then definitely my model would have either thrown up an error, or my model would have been inaccurate. Okay, so now education. In education, I don't see any problem. Okay, so there are these many number of categories are there in in the education column. Then marital status. Okay, all right. Then occupation. In the occupation, again, there is a question mark. So again, these are the missing values. It shows that there are good enough of number of missing values, existing in my data. So again, in the country, native country, there is some question mark of for 583 observations. And finally, this is my output variable. Okay, so I have two categories, okay, in my output variable. Now, you can do further analysis on the basis of like, you know, to find out what is the composition of each categories. Okay, so for that, I'll take the count and then divide by total number of observations. So here in this particular column, work class, the private category is having around 70% of the observations, and remaining, there is very less number of observations which are falling in other categories, right? So with this also you can understand, is there any kind of a dominating categories existing in your data? Okay, and if yes, then what is that category? Okay, so even by the count you can find out, and either or else you can go and calculate the percentage. Look at this particular column, native country. 90% of the observations falls under in United States, and there are so many other countries, but there is a very few observations which are falling in, which have been labeled as other countries other than United States. So this will give you some idea about the data set. Okay, is there any kind of imbalanced, is it an imbalanced data set? Imbalance means if in any categorical variable, one category is kind of taking the majority of the proportion of the data set, and the other category, there is a very minimal representation of the other categories, then that is known as imbalanced data. So here the native country is completely imbalanced data because 90% of the observations are falling under United States, right? Okay, so now I'm taking this particular variable work class and let's go and deal with it. So here I'm printing the unique categories just for this particular variable. So these are all unique categories in which I have question mark also. Now I'm going and counting this. So there is a question mark here. Okay. Now what I'm doing is now I am treating the data now. So now here I am going and replacing this question mark with the NaN values. NaN is not a number. Not a number, and that too, it is a specific, what do you say, object you will find in NumPy package. Okay. I'm replacing with that. So here I'm saying this particular column, I'm using this function dot replace, and here you have to specify which uh, what character, okay, you want to replace. So here I want to replace question mark, and here you have to specify with what you want to replace. Either if you know, if see, for example, this is question mark. Sometimes what will happen is most of the observations are falling under private. Okay, so now this is the mode, right? What do you mean by mode? The most, the highly occurring category is considered as mode, right? Or the high most frequent value is considered as the mode. So here, out of total number of observations, most of the observations are falling under this particular work class known as private. So even the question mark, you can replace it as private. Okay, that is also one of the technique of dealing with the missing values. So currently what I'm doing is I'm just first replacing this question mark with np dot nan. So nan is an object, you will find it in NumPy, and if you replace it with this, then this Python codes will identify, yes, there is any missing value in the data. In place equal to true means it will replace. Okay, in place of that question mark, it will replace it at true. Now sometimes you will see the problem. Okay, so you have seen the data here, and then you will see that, okay, there is a question mark, and you will put the question mark here, and then you will go and say replace. Sorry. That one. Just a second. Okay, so I ran this code. Now again, I go back here and run this. Still that question mark is here. So what is the problem? Okay, now you have to go to the original data set in Excel. And in Excel, if you go and check, you will find that there is a space also before this question mark. Now, if you give a space before this question mark, now it will identify this character. And then see it, earlier, when I ran that, it didn't give me any error also. Okay, so if you are automating the entire pipeline and if you don't fix this particular problem, though the code will not give you any error, but that changes and all those things will not reflect in your data. So you have to be very cautious that you run this, execute this particular line, and then again check, okay, whether that change has been done on your data or not. So if I'm running this now if you observe this, this question mark should go away now. Yeah, so now there is no missing values. Sorry, there is no question mark category now here. And if you go and say easenull.com, here, easenull.sum, now it is giving me 1836. Earlier there was a zero. Okay, it was zero because every value it was counting it um, as a standard values. Okay, and it hasn't been it hasn't identified whether it is a question mark or the genuine value. So this is how you can replace some special characters if it, or some junk characters if it is existing in your data set. Similarly, what I'm doing it for every column. Here also there's a question mark. I replaced it with nan. So now the question mark uh, got disappeared from here. Okay, so let me run all these things and then I will show you. This we have done here from here. Run. So same steps, guys. I'm doing it for every column wherever there is a question mark, right? Replaced. This is replaced. Now, if I go and say df categorical is null.sum, on the top you have seen, right? When I've used this, every value was coming out to be zero. Now, if I run this, so wherever I have replaced in this particular column, I have replaced work loss, occupation, I have replaced in the native country, I have replaced, right? So now this np.nan has been identified by this code. And here it is showing that there are 1836 observations which are null, okay, which not a number in work class column. And 1843 observations are missing in this occupation column. And 583 values are missing in this particular column. Okay, so now in the native country, okay, this particular column, look at this, how many categories are there? Now, in any particular column, if there are more number of categories, then it is called as high cardinality problem. Okay, so here the number of labels are more in for this native country. Okay, and this is known as high cardinality problem. Okay, when there are high number of labels in particular variable. So you must be knowing that, okay, if there is more number of labels, generally what we do, we group them into a different category. For example, we put them into others, right? Typically we do that. So that is one way of doing it. So if you want to check how many number of categories are there, and based on that, if you want to find out which of the variables are having high cardinality, so you just use this particular for loop and it will give you the number of labels in each of the variables. So here for this native country, we have 42 labels. Now, this is going to be a problem because I mentioned, right, these categorical variables we are going to transform. We will do some kind of feature engineering. And what we will do is that for every label, we will add a separate column. So if there are more number of labels in particular variable, then that many number of columns we need to add. So that's going to be um, a, a big problem. Okay. And in this case, you might have seen that even the other labels or other categories, they, they do not have much observations marked with that particular label. In that way also, these are not that important labels, so we can group those labels. Okay, so in that case, so what we are going to do is okay, so we will see what. So we will deal with that high cardinality when we are doing when we do the transformation. So before that, let's also explore the numerical variables. Now, till this part, we have explored all the categorical variables. We have seen how many labels are there, what are those labels, how much proportion of those labels are existing in our data set. Then we have also checked, is there any missing values or any other special characters existing in those variables. We have dealt with that. Now we will go and explore the numerical variables. So here the same method. So here the D type, I will mark it as not equal to O. So not equal to object. So other than object, whichever variables are there in my data set, they will be considered under this particular object known as numerical. So there are 6 variables now. Okay, age and this final weight or education number, capital gain, and all those things are the numerical variables. Now this is how my numerical variables look like. Now I will go and summarize. And again, here also I will find out some missing values. So let me go and check, is there any missing values? Okay, so it is saying 0, 0, 0, 0. So see, if the values are in your data set is marked as 0, it will not consider as missing values, guys. Okay, then you have to go and explicitly, then you have to tell the Python code that anywhere if the cell value is equal to 0, then you consider that as a missing value. So that you have to tell it explicitly. But automatically it will not detect as a missing value. If that cell is blank, if there is no value existing in that particular cell, then only it will consider as null. Otherwise, it will consider as a genuine value only. And even you have to check with the business only, wherever it is 0, is it like, it is really a 0 or is it a missing value? Okay. So for example, typically when we do that sales forecasting, in some of the days would be missing, okay, in the data. And what we do is we add those days and then we put the value as 0. So we will go and check with the business, is like the data missing, or is in that particular day there were no sales. If there is no sale, then 0 is the genuine value because there is no sales. If the date is missing and somehow they haven't tracked, or they haven't measured and uh, captured that data, then that is considered as missing value. Okay, so we have to find out, we have to understand the 0, why it is 0. Is it because there is no value there, or is it really a 0? Okay, in that particular scenario. Okay, so now, okay, so there is no problem with this numerical column, so it's look good. Okay, now what I'm doing is I'm segregating the input and the output column. So here in the input column, in the input variables, rather than selecting, what I'm doing, I'm dropping from the entire data set. I'm dropping this income. So remaining all the variables would be my input variables, and the output variable would be DF income, right? So these are all my input columns. Now, next is the feature engineering. So first, let's understand what do you mean by feature engineering. And again, this is from the interview perspective. Again, it's very important for you to understand. As I mentioned, this feature engineering or data pre-processing, it takes a lot of time. And you have seen, right? Till now, we are just talking about the data pre-processing only. We haven't gone into the model training. So typically in any real scenario, this feature engineering and data pre-processing is the most tedious, time-taking, and the complicated step. Okay. So even in the interview, people may ask, like whenever you are talking about any particular project, rather than focusing more on the model training, they will focus more on the data pre-processing. Now you tell me, they will ask like, now you tell me, okay, you got the data. You got the data from the real data, from your databases or from your data sources. Now, what kind of discrepancies have you found and how you have addressed those discrepancies? Okay, and what level of feature engineering you have done, how you have dealt with the missing values, how you have dealt with the outliers. Okay, those kind of questions, people would ask. They would be more interested, because until and unless you don't know how to treat the data, how to curate and cleanse the data and prepare the data, you won't be able to train your model well, right? So that's the reason it is a very critical step of model building. Okay, so feature engineering. So I have the categorical variable, I have the output, I have the numerical variable. Okay, so categorical variable, again, I'm selecting numerical variable, again, I'm segregating. Okay, so in the categorical variable, there are certain null values. Okay, we have seen, we have in the work class, we have in the occupation, and we have in the native country. So now out of the entire missing values in my data set, I want to see in which particular column there is more missing value. So I'm here calculating the basically the proportion. So why is it important is because if in any variable, if there are more number of missing values, sometimes it's good, to drop those columns. Because see, even if you replace with some arbitrary value, or if you just consider as is, that variable would not be of much importance because the values are missing, right? So that would not indicate or would not give any information to the algorithm, to learn any patterns. So in that case, you can ignore. So if there is, for example, if there 10 more than 20% or 30% of the observations are missing, then you can ignore those variables. So these are okay. These are not much missing values are there, so I can go and treat that. Okay. So what I have done is here there is a function again in pandas, fill NA. Okay. So there is another function like drop NA. So if you want to drop, just say drop NA. So all the missing value observations will be dropped. If you say fill NA, then it will go and fill the value. Okay, some value with that particular NA value. Okay. So what I'm doing is I'm filling this with mode. As I mentioned, the mode is the most frequent category in the data. So it will go and fill that particular NA value with the most frequent value. So for every variable, wherever there is a missing value, I'm replacing with the mode. Okay, so this is known as missing value imputation. So I'm imputing some value with that missing value, with that NA. So typically in the categorical variable, we replace the NA values with mode, and in the numerical columns, we replace it with mean. Okay. So mode imputation, mean imputation, these are the most popular techniques which we'll use for replacing NA values in categorical variables and the numerical variables respectively. Okay. So now earlier, if I run this, where it is gone? Yeah, if I run this, 1 second. Yes. Income is not an index. See, now there are missing values in the work class, occupation, and the native country. Now I'm going and replacing it with the mode. I'm running this. Now all the missing values gone. Now this is the genuine result now. Now you will not find any question mark or any blank values, nothing. Okay, so now your data is complete. Okay, so this is how you should um, deal with the missing values, or if you have any junk values existing in your data set, you have to clean it, you have to replace it, and that's how you have to um, prepare your data. Now comes the most important part of the feature engineering. So here we call as encoding categorical variables. So what does that mean? Okay, so let's suppose in a particular categorical variable, there are four categories. And let's suppose those four categories, here if you see, this is private, this is self-employed, okay, bachelors, all these are like string values. And whatever algorithm we are discussing so far, all those are like arithmetical based algorithms, right? How those algorithm would work if the values are text, right? It would not work. Now, what can we do? So we call it as a encoding. So what we can do is we encode each of these categories by some number. So for example, self-employed, we can label it as 0. Private, we can label it as 1. But there is a catch. Okay. If the private, I label it as 1, self-employed, I label it as 0, then higher importance would be given to those categories which are labeled by higher number, right? So to avoid that, what we will do is for every category, we will add a column. So for example, for self-employed, there would be a separate column. For private, there would be a separate column. Okay. So for example, the first observation has been labeled as self-employed. Then that particular column, self-employed column, will be marked as 1 and the private will be marked as 0. Okay, so this whole process is known as one-hot encoding. So something like this. Okay, so in the work class, we have these 1, 2, 3, 4, 5, 6, 7, 7 labels. So it has created 7 different variable. Work class underscore local government, work class underscore never worked, work class underscore private, and so on and so forth, right? So if the first column has been labeled as self-employed, then it will be marked as 1, so which is nothing but the true, and other columns will be marked as false. So this is known as one hot encoding process, or else we call it as creating a dummy variables. So now this is considered as a numerical because, as I mentioned, the false in the backend, it will be encoded as 0 and the true will be encoded as 1. So on this particular data, arithmetical calculations can be done or the numerical operations can be done. Okay. So where they were, so all these observations have been marked as private. So there's the reason this particular column has been labeled as true, 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 true for all those observations. So like that, we have done it for all the categorical variables. Okay. So now, for doing that, in pandas, we have one function known as get dummies. Okay, so dummy variable. So these variables are called as dummy variables. Okay, so why it got named, so I'm not sure. But they call it as dummy variables. So here you pass all the categorical variable, and here we are dropping the first equal to true. Now, why we do that? So, for example, in the work class, how many categories are there? Let me go and check. Yeah, in the work class, we had 9 labels in which one was question mark. So typically there is eight labels are there. But when we are dumbing it here, creating our dummy variables, how many we got? 1, 2, 3, 4, 5, 6, 7. 7 only. One is missing. Why one is missing? Because here we mentioned drop first equal to true. So here one particular class, one particular label we are dropping for every category. Why we do that? See, if all the 7 categories are labeled as false, then automatically it's implicit that okay, the eighth category, it would be the eighth category only. So for that reason, we drop one particular variable. Okay, because if all the other categories are labeled as false, then it has to be the eighth category. So there's no point of adding one more eighth category. So it is implicit, right? If all are false, then that would be true. So that's the reason whenever we are creating the dummy variables, we create n minus one dummy variables. If we have n categories, then we create n minus one dummy variables. So for every category, it is created in that way. So it is not showing the entire data. If you see dot dot dot, so it is just showing the high level data. There are so many other columns also. So now the new shape of this particular column is 99 variables. So you know that for country we have 42 labels. All so many labels are there in every category. So overall now it has come to as 99 variables. Earlier it was 15. Now it has changed to 99. So now it is going to be a big high dimensional data which we have to deal with. Now here, now I'm going and doing the feature scaling. You know about feature scaling, right? So here, if you have seen that now some of the columns would be labeled as 0, 1, 0, 1, 0, 1. And there are some numerical variables which are at a very high scale. Okay, so like here, and there are age columns which is at a lower scale. So the data is present at various scale. Okay, so if you find that data is too much of difference in the scale, then it's always better, go and perform the feature scaling. So feature scaling, it's a method, which will convert all the variables into the same scale. Earlier in the use cases, we have used the standard scalar. Standard scalar formula is that z score, x minus mu by sigma. Here we are considering a different scaling technique known as normalizer. The normalizer formula is x minus minimum divided by maximum minus minimum. Okay, so that's the formula. Okay, I will explain you in the next class again. So this normalizer, just consider that this is one of the scaling technique. Okay, I'm using the normalizer here. And just the way I have performed the scaling in other use cases before, similarly, I will use this particular scaling technique here on this data. First, I will fit and then transform. So all my data would be converted into the same scale, something like this. Okay. And here I'm just going and describing the data. Here, if you see, the minimum value would be 0, 0, 0, 0 for all the values. Okay, and the maximum value is also kind of in the same scale. Okay, and the minimum is also 0. Standard deviation. Okay, so not much difference I'm finding out in the data now. So this is okay. Now, so this is my entire data, actual data now, which has been transformed. Guys, you can stop me anywhere if you're not following me. What we have done is first we have converted all the categories into a dummy variables. So after creating a dummy variables, I perform the scaling to convert all the variables into the same scale. Okay, the values to the same scale. And after that, I'm splitting the data into two parts, training and test. And now I'll go and perform the model training. So here, you must be thinking that, okay, where is that frequency table? Where is that likelihood table and all those things, right? So everything, will be taken care inside this algorithm. You need not to worry about anything. Okay, just you have converted. And here we are using a special naive Bayes algorithm known as Gaussian naive Bayes. Gaussian is a statistical word which uh, which represents or which which is defined as a normal distribution. So Gaussian distribution and the normal distribution, these are all synonyms. Okay, these are same words. Okay, but in some of the statistics, okay, people call the normal distribution as a Gaussian distribution. Okay, so here it is a Gaussian normal naive Bayes which we are going to use. And as we have already normalized the data, I am assuming that all these variables will will have a normal distribution. Okay. Now, once every variable is having a normal distribution, what this Gaussian Naive algorithm would do is it will break that entire distribution into uh, equal parts. So, for example, for the text classification, it's not a problem, but for this numerical data, you will see this all these things happening, okay, inside the algorithm. Now, this is my normal distribution. Now, what it will do is it will break this distribution into equal parts. Now, how this naive Bayes algorithm is do is, for example, now it will create the frequency table of every column. So, for example, now this is one part, second part, third part, fourth part, fifth, sixth, seventh. First part, second part, third part, fourth part, fifth part. Now there would be another variables. Okay, and similarly there would be another parts also. Like, okay, if the data is in this part, the value is in this part, one part. For other category, how many number of values were falling in the first part, so that it will put it here. So 4. So for example, there is another features normal distribution. If this particular value is falling in this particular zone, how many times in this particular variable 2 the values were falling in this particular section? Okay, so that count it will take it. So here, if the values are here, how many times the values in variable 2 were falling in this particular section? It will count it here, for example, 5. So like that, it will create the frequency table for everything, and this would be the total number of observations. So like that, it will create the frequency, this kind of table, for the entire data. And based on that, it will generate the likelihood. So for example, the total number of observation is 100. Out of 100, the 4 variables are in this particular. Then what is the likelihood here? It is 0.04. Okay. So likelihood is 0.04. That means there is a 4% chance that if the value is falling in this particular section, then in this variable 2 also the value will fall in this particular section. So firstly, what we have done is we have converted all the variables, because all these are numerical variables now. So all the numerical variables, firstly, we converted that into a normal distribution. And this Gaussian naive Bayes what it will do is it will convert all these distribution into equal parts. And then based on that, it will create this frequency table. Now, once the frequency table is created, now based on this, it would be easier, to apply the Bayesian Bayes theorem on top of that to calculate the probability of to calculate the posterior probability. Okay, so model training part, see how easy it is. Okay, has only 3 lines of code. You first import that particular algorithm. And in sklearn, we have a different module altogether. We have a different module altogether, which is known as, okay, which is known as naive Bayes. So here, all the probabilistic based algorithms, you will find it in this particular module. So you can go to that scikit-learn website, and in that, you will find all these different algorithms which are under naive Bayes module. You will see all are listed there. So here from this naive Bayes, I have imported a very specific naive Bayes known as Gaussian. So if you are encountering, or if you are having a numerical data set, something like this, then better you go with a Gaussian naive Bayes. So first I initialized that particular model, and then I have fit that model onto this training data set. So once it is done, that's all. Okay, your job is done. Okay, you go and predict it. and this is how it will give you the predictions. If you directly use dot predict, it will give you the classes. If you want a probability, then you say predict underscore proba. Okay. So here I'm comparing with the actual. So with this model, I got 81% accuracy, which is not bad, which is pretty good. Okay, so this is the accuracy which I'm getting on my test data. Okay, so now I'm finding out on the training. On the training, I got again 81, and on the test also I got 81. So that's good. So it is not an overfitted model. Okay. Okay. So null model, right? Null model for any classification is that, you just consider the mode, okay, and then you label all the columns with that mode. And in the numerical prediction, you go with mean, and that would be your null model. In the regression classes, linear regression, logistic regression, we discussed what is null model, right? So here, the null model, if I'm going with null model, I'm getting 75% accuracy. So see, here in my data set, this particular category is the majority category. Out of the total observations, um, uh, 7,454 observations in this particular test data set have been marked as less than equal to 50K. So without doing anything, what I'm doing is whatever new data points are coming, I'm labeling them as less than equal to 50K. Let's suppose if I've done it on the test data set, so this is the accuracy I would be getting. Okay, 75%. So this is important for you to see that how good your model is when compared with your null model. If your model is equivalent to your null model or worse than your null model, then your model is of no use. Okay, because it is not doing anything greater than the null model, right? So here the null model is giving 76% accuracy and my model is giving 81% accuracy. So it is 6% more than the null model. Then after that, I will go and use all those evaluation matrix, confusion matrix, and all those things. So this is my confusion matrix, or else you can plot, in the yesterday's class, we have used matplotlib and we have created a very good confusion matrix. Okay, even you can do that. Or even you can use this heat map to have a confusion matrix like this. So these are actual positives, actual negatives. These are predicted positives, predicted negatives. Okay. So you can create a confusion matrix like this. In this we have already seen, you can print the classification report, which will give you the recall and precision. Now, whatever formula we have discussed, right, in the initial class, all that thing I have, you know, uh, all that formulas I have used here, for calculating the accuracy, for calculating the error, for calculating the precision, the recall, along with the some definition and the formula around it. So you can go through it. Now, so there is a true positive rate. So there is a altogether a new what you say we talked about recall, right? So even the recall is called as true positive rate, because what is the formula of recall? Recall is true positive divided by true positive plus false negative. So sometimes the recall is also called as true positive rate. It is a synonymous with recall, and it is also called as sensitivity. Okay, so there is many names to this recall word. Okay, somewhere people may also called it as sensitivity. Somewhere people may call it as true positive rate. Okay, now then we have a false positive rate. Now I'll tell you why I'm talking about true positive and false positive. Okay, so calculating the false positive, this is the formula, which is FP divided by FP plus TN. Now, specificity, there's another word known as specificity, which is 1 minus false positive rate, which is true negative divided by true negative plus false positive. Now, this specificity is also called as true negative rate, where recall is called as true positive rate or sensitivity. Specificity is also called as true negative rate. Okay. So, why I'm talking about all these things? With this comes another concept known as, this I will cover, known as ROC. So, ROC is another one tool or technique with which we basically understand how the model is performing, okay, and that too visually because it is a curve. ROC is, in short, it is called a receiver operating characteristic curve. So even in the interview, people may ask you what do you mean by ROC curve, and how it is created, and what kind of information we will get about the model performance through this ROC curve. Okay, so this receiver operating characteristic curve. So generally, this whole idea of this ROC curve has been taken from the Navy. Okay, in the Navy, people used to monitor the signals. Okay, and while monitoring the signals, the SOS signals will be passed, right? You know about SOS signals. If there is any kind of emergency, people pass the SOS signals, for some help. So to classify how many signals are true positives and false positives, they used to use this ROC curve. So with that concept, the same concept, we are using it here. Okay, so that's the reason the name has been given as receiver operating characteristic curve. Okay. Now this ROC curve is plotted between the true positive rate and the false positive rate. So what is true positive rate? We have just discussed the true positive rate is also called as recall or also called as sensitivity. Okay. The false positive rate, FPR, okay, you can also write it as, if you go here, can we write false positive rate as 1 minus specificity? See, if you do 1 minus specificity, you will get this false positive rate. Okay. So this ROC curve is a curve between sensitivity and 1 minus specificity. Or in short, you can say that it is a graph between true positive rate and the false positive rate. So these graphs look like something like this. Okay. So true positive rate, which is known as sensitivity, and the false positive rate is your x-axis, which is 1 minus specificity. Okay. You can refer to the formula above. Okay. And it is there in the handouts also. You can see. Now, this is how your graph would come. Okay. For this particular problem, okay, this is how my graph is coming. Now, how you should read this? This entire area of this particular graph is equal to 1 because it is a square, right? Your true positive rate would range between 0 and 1 because it is a rate. Okay, it is a ratio. So it will be ranging between 0 and 1. Even the false positive rate will range between 0 and 1. So it is a square. The total area would be equal to 1. Now, we have to understand how much area is being captured by this blue line, which is my model performance. Okay, so if my curve will touch to this particular corner, so that means my model is giving me closer to 100% accuracy. Okay, the performance close to 100%. Now here, if you see this particular uh, turn of this particular curve, it's kind of showing around 80, right? So even we have seen the accuracy is coming out to be 81, right? So it is, this ROC curve is also showing something like that, more around 80% accurate is your model. This middle line is like 50%. Okay. So if your model line, this blue line is somewhere closer to this dotted line, so that means your model is of no use because it is a 50% accurate. So you have to make sure that your model, this particular blue line, should be as far to this dotted line and as close to this particular corner. Okay. So in that way, it shows that your model is a good model. So for that, either you can visualize or you can look at this particular chart and you can comment about the model performance, or else you can calculate the area under the curve, which we call as AUC. So here it is, ROC AUC. It stands for receiver operating character area under the curve. So here in sklearn, we have a function for this ROC AUC score, and you need not to do anything. You just need to pass the actuals and the predictions, and it will give you the area under the curve. Now it is saying 86%. 86 is the 0.86 is the area under the curve. As the total area of the square is 1, now 86% of the area has been captured by this particular model. So it says that 86% of the variance has been captured by the model. Okay, so that's how you can comment on the model performance. So this is a pretty exhaustive code, and I have tried to uh, include as much as possible the explanation of this particular code. So go through it and understand this, because there are so many different things what we have done in this particular example. So go through step by step and understand what we have done and why we have done and how we have done. So that you will understand the entire picture about this. Okay, so here we have also given the interpretation of this particular ROC AUC. And then finally, the K-fold cross validation technique. Okay. So, but before that, okay, let me know anybody has any question. So step by step, if you see that we have loaded the data, then we have analyzed the data, then we have found the discrepancies, then we have dealt with those discrepancies. Then we did some kind of feature engineering. In feature engineering, we have replaced the missing values, and then we have created the dummy variables. Then after that, we have trained the model, and after training the model, we have evaluated the model. And during the evaluation, we have added a couple more evaluation metrics also, along with the ones which we have discussed earlier, and then we have evaluated the model. So far, we have discussed all these things. Now, what is this K-fold cross validation? Now, this is another technique of evaluation. I've talked about overfitting problem, right? Um, so what is overfitting? If my model is performing good on my training data set, but does not perform well on my test data, then that is known as overfitting. Okay. Now, it's important for you to validate it and before going into a production. Okay, before pushing that model into a production. So one way is like you just directly test it on your training data set and the test data set, and then declare that this model is good. Or else, if it is a very critical scenario where you have to be very sure that your model will perform better in the production environment. So there it is always better if you validate that model multiple times. Now, validating the model multiple times is known as cross validation. Is known as cross validation. Now, how many times you want to cross validate, that depends on the number of folds you decide. So there's a reason it is called as K-fold cross validation. So what this technique is all about, okay? So now you have seen where you have one data set. Okay, now this is your data set, let's suppose. And now you divided that into two parts, the training and the test. Okay. So 80% you have taken into training and 20% you have considered into test. Now this is the technique which we are being following, for all the use cases. Now, this method is known as holdout method. This is the most simpler method, and in any of the use case, if you don't want to, if it is not critical, then you can just directly train your model on the training data set and test it on the test data set, and then take the decision. But if it is like critical, then what you do is you go for this k-fold cross validation, where you do the testing multiple times. Now, here, whatever k value you decide, for example, I decided 5-fold cross validation. So what it will do is it will divide the data into 5 equal parts: 1, 2, 3, 4, and 5. Okay. Now, and it divides the data into 5 parts, and it will run also 5 times. In the first run, what it will do is it will consider one part as your test data set, and the remaining part it will consider as a training data set. So 4 parts for training and 1 part of the data set for test. in the second run, what it will do is it will consider a separate part as test. Now here in this case, it will consider this part as test. In the third run, it will consider this part as test, and remaining parts it will consider as training data set. So if you see that in every run, okay, it is considering different data set, a different training data set, and different test data set. So what you're doing is you are validating on every different test data set that how it is performing, right? And then here you will find out the accuracy. For example, on the first run on the test data set, it has given 85% accuracy. On the second run, it has given 82% accuracy. Here it has given 81. Here it is given 86. Here it is given 84. So that means it is a stable model. In every run, it is kind of giving me the similar results, okay, similar equal results. But what if the model sometimes like giving 86% accuracy, and sometimes it is giving 64% accuracy, sometimes 71% accuracy, sometimes it is like failing miserably and giving 44% accuracy, and somewhere it is giving average like 75% accuracy. Now, which model would you choose, model 1 or model 2? Of course, model 1 you will choose because it is consistent. Okay, it is consistent in every different data set. On every different data set, it has given a pretty good consistent results. Okay, somewhere close to 80 to 85% accuracy. So now this, if it happens in this way, now you have you have confirmed that this model is a robust model. It has neither overfit, it is neither overfitted model, neither nor underfitted model. So this cross validation technique is important if you want to verify whether your model is a overfitted model or underfitted model. If it is an overfitted model, on some of the data set, it will may give you a better results. Okay, if it is an underfitted model, in some of the cases, it may give you a very bad results. Okay, so instead of giving sometimes good results, sometimes bad results, if it is giving me the consistent result, now that is considered as a better model. So this is also one of the evaluation technique which we use, okay, when we have to test the model, whether it is good or bad. So here we are going with this k-fold cross validation for the same thing. Here I am using this particular algorithm, GNB, which is Gaussian Naive Bayes. And here there is a function available in this model selection, cross val score. And CV is cross validation. I'm going with 10-fold and scoring. Okay. How I'm evaluating the model? I'm evaluating the model by accuracy. So this is how my on 10 different runs, my accuracy looks like 81, 80, 80, 81, 82, 80. So very consistent results. Okay. I'm getting over 80% accuracy and somewhere between 80 to 82. Okay, so in that way, my model, I confirm this model is a robust model. Now I can deploy this model in production. On an average, my cross validation score is 81%. Okay, so there is an interpretation. So now this is the full-fledged code, full-fledged use case, guys. Okay, where we have starting from the data pre-processing till the model evaluation, we have kind of covered every aspect. Okay, and now once the model is confirmed that it is good, now you can push it to production. Okay, so now I'll stop it here. Let me know anybody has any question. So go through it. Probably after going through the code, you may get certain questions. Okay, so please do ask me, okay, in tomorrow's class. Okay, so if we are good,
Sir, is
then
this
yeah.
a job of data scientist, or all the steps are the job of data scientist, or any other persons will be?
Yeah, see, consider this is a job of data scientist only. Sometimes what happen is if we have to, at the enterprise level, if we call the concept as data lake. Okay, what is data lake is where the all the entire data of enterprise will get dumped into one common repository. Okay, that we call as the data lake. So sometimes in enterprise, what they will do is they will create a multiple zones or multiple layers in the data lake. The first layer will be having all the raw data. Second layer will have the cleansed data. Okay, the quality of that data will be improved. The third layer would be the presentation layer. In the presentation layer, whatever data is required for the consumption, only that particular data will be saved, not the entire data. Now, if the enterprise is following all this data governance and all they have a good data platform, then it will be the job of data engineers, to look at all the missing values and then curating those values, removing the junk values and all those things. So if it is like in-house implementation where you have a good org structure, where you have a data team, data engineering team, and data governance is in place, then all these things like cleaning and data curation will be taken care by data engineers. But if you are into a services company where the data will be given by the customer and you're not sure how the data would be, okay, and you have to build the solution, then it would be your job as a data scientist, okay, who have to perform all these different tasks. So here I got just the Excel sheet, okay, and I cannot go back to customer and say that okay, clean it and then give me, right? So I have to perform all those cleaning. And this feature engineering, like creating a dummy variables and all those things and scaling and everything, it is pure data scientist job. Feature engineering is the data scientist job. How to replace the missing values and what scaling needs to be done, creating a dummy variables. All it is data scientist decision, and they only have to do it. The data engineers, what it will do is basically all the duplicates. So the normal cleansing and curation part, okay, if there are any duplicates, they will remove the duplicates, or if there is any kind of an outliers, then they will try to remove those outliers. So they will do first level of cleansing, okay, and they will build pipelines. So as a new data set hits the data lake, those pipelines will get invoked and they will do the cleansing, and then they will push that data into a second layer, which is known as curated layer. Okay, and from there we have to fetch the data as a data scientist, and then we have to do all that analysis and then push it back to a presentation layer. And once the data is sitting in the presentation layer, now you can push it to applications, that data, or else you can build dashboards. So whatever way you want to consume that data, you can consume that data from the presentation. Okay. So in different scenarios, the job, the responsibility may change. Got it?
Yes.
Any other questions? Okay, then all right, guys. We connect tomorrow then. Thank you. Take care.